We're trying to show that if p is any prime greater than or equal to 7, that p to the 8th is congruent to 1 mod 240. Now, another way of stating this that I think is perhaps a little more useful in this context, that's the very same thing as saying that the number 240 is a divisor. Okay, and that's what this vertical bar means. It's a divisor of p to the 8th minus 1. And y'all, p is a prime number. Let me go ahead and envelop that in parentheses. Okay. Another way of saying this is that p to the 8th minus 1 is a multiple of 240. Now, the prime factorization comes in very, very handy. 2 to the 4th happens to be 16. But let's go ahead and handle the cases 3 and 5 first. Now, there's a result called Fermat's little theorem. It goes like this. Let me use another letter here. It looks like this. If you have an integer a that is not a multiple of a prime number, let me just write it. Let's use q just to avoid any clash of symbols here. A to the q minus 1, where q is a prime, is congruent to 1 mod q. And again, q is a prime. Okay, mod q. All right. And so you see we did that right here. 3 is a prime, so this would be 3 minus 2 right here. 5 is a prime. 5 minus 1 is the 4 that you see right here. So you see both of these statements are just immediate consequences of Fermat's little theorem here. And again, this is a true statement as long as a and q are relatively prime. Let me write that down. A and q are relatively prime. Some people say that's co-prime. They don't share any factors. Okay, so now notice that this also implies since we have these things in congruence form, we can treat a congruence just like an equality. So if you multiply this equality against itself 4 times, you end up getting p to the 8th. You can think of that as raising it to the 4th power also, but you get p to the 8th is congruent to 1 mod 3. I hope you see that analogy. It takes a little bit of proving, but the equality acts like the congruence acts a lot like an equality, and so we can raise both sides of this equality slash congruence to the 4th power, or just more naively, you can just multiply it against itself 4 times. Okay. Now we also have to assume that p can't be equal to 3. P is not equal to 3, and it's clearly not. I mean, you can just check it. If p is equal to 3, you get 9 minus 1, which is 8, which is not divisible by 3. But that's because it doesn't satisfy Fermat's little theorem. P is congruent to 0. All right? P is congruent to 0 mod 3. But you can just check it if that doesn't make any sense. If p is equal to 3, you get 3 squared minus 1 is 8, and that's not divisible by 3. Now, right here, if you multiply this by itself twice or square it, you get p to the 8th is congruent to 1 mod 5. Okay, and here, and y'all right up here, I should have said p cannot equal to 3. All right, and in a similar fashion, p can't be equal to 5. And you kind of see why we started at 7 up here for the problem statement. All right. Now there's another result that's going to help us out with 16, or 2 to the 4th. Now there's something, it's called Euler's Totient Function. Let me write out just the general way that would look. We'll just use a again. There's something called the Euler's Totient Function, which counts the number of values relatively prime. And I'll show you precisely what that means. Now let's see if I can even make this symbol here. A to the, what is that thing? That's called phi, I think. So I'm going to try to make a phi here. Not too good, is it? All right, let's come down. Okay. So a to the phi, let's use whatever you want. We can use n. A to the phi of n is congruent to 1 mod n. And the condition as before, similar to before, is that A and n are relatively prime. A and n would be relatively prime. Now, so what does this function do? It counts all the numbers less than 16 that are relatively prime to 16. Now, I'll just list those right above it here. Phi at 16 you would be talking about the numbers. You see, all the odd numbers are going to be relatively prime to the even number 16, right? 1, 3, 5. And you can just, you can see that it's going to be 8, but I'll just write them down. All of these numbers, which are the odd numbers less than 16, they're relatively prime to 16. 13 and 15, right? But we're counting them. We're not adding them or anything. We're counting them. So how many of them are there? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, right? So that's where this 8 comes from. And this is just a general result right here. So you see, we get what we want. We get p to the 8th is greater than 1, provided p is not equal to 2. Okay? So we have to write down p not equal to 2. Okay, again, and that's to satisfy this condition A and n have to be relatively prime. All right? So you see, we have we have three conditions here. Notice that we have, I'll just write them in order here. We have 3, and to save a little bit of writing here, folks, I'll just write 3, 5, and 16. Okay, all of them divide p squared, or p to the 8th minus 1. So I'm looking right here. Divides p to the 8th minus 1. Okay, and that's what we're trying to show here. This 240 has to divide p to the 8 minus 1, but remember, 16 times 3 times 5 is 240. And we've just shown that these 3 steps we just went through shows that 3, 5, and 16 divide p to the 8th minus 1. Therefore, the condition we're trying to prove is true. That is, another way of stating this is p to the 8th is congruent to 1 mod 240. And that proves what we're trying to prove. So it's Fermat's little theorem, along with what they call the Euler totient function, that got the job done here for us. Now, just a concrete example here. Notice that 13 to the 8th, I did the I just used a calculator here. For 13 to the 8th is equal to 815 million, yada, yada, yada. Now, 13 to the 8th minus 1 is going to equal to, I'll go ahead and write it down, 815, 730. And then when you subtract 1 from that last part, you'll get 720, right? So if we divide this by 240, now I don't know what that is, but it's guaranteed to be an integer, folks. And it's not hard to believe if you take a look at 240 divides 720, right? And you can, it doesn't take much work to show that 240 without a calculator divides 815,730. So again, this is a member of the, this is a member of the natural numbers. Okay. It's a member of n. So that is a concrete example where we use p equals 13, and of course 13 is greater than 7, which that was our break point for this problem. But anyway, this is what we're trying to prove. We proved it. And then here's a concrete example of it working out for a prime number larger than 7. All righty. Thank you for viewing.